bugbear of classical mechanics, and I thought I'd try to explain some of the simple aspects of it by doing a very simple problem, namely well, some kind of bead or ball sliding object constrained to move on a parabolic curve, not too different from the problem I've given you that's requiring you to move on a cycloid and then an inverted parabola, and then actually a constrained problem that involves something rolling off of a sphere. The ways to do this are numerous, and I'm going to show basically 4 different techniques that involve constraints. And I'll start with the easiest one, the one that's the most obvious, the one that very often you try first, and for qualifying exams almost always works. The other ways may be able to do it more conveniently and quicker, or they may not. They may make it much more difficult, but have some advantages. So what we're going to discuss are those aspects of this very simple case. So let's begin here. What we call way 1 is to just take your Lagrangian and hope that you can convert constraints into part of a single Lagrangian involving one dimension. In this case, we're converting it so that the independent variable is x, the abscissal coordinate. And I'm just doing the replacement here of the constraint being the equation for this particular parabola, and its derivative with respect to time. So sticking in y prime for that, and then we're going ahead and sticking the y value in here. Then once you have that, it's a one-dimensional Lagrangian momentum and force. Those are the 2 Lagrange equations that we have. This one being px dot, partial L with respect to x, the other one just being definition of momentum. So the Lagrangian that we have here simplifies a little bit, makes clear the coefficients. And the momentum becomes kind of weird. We saw this with electromagnetic fields. In a sense, that's a funny kind of dynamic constraint. Instead of getting the momentum equal to mv, we get this other term in with a mix. And the force on this, the partial derivative of this Lagrangian with respect to x, is this term here and that term there. And we have a product of coordinate and velocity squared, in addition to the usual force that would be a Hooke law force, F equal constant with a minus sign times the distance x. So what we do is take the time derivative of the momentum. Remember when we went through the first time we used Lagrangians, this was sort of toward the end of the calculation, and setting that equal to the partial derivative of L with respect to x, namely that weird force there. So this is basically what we've got. So we look to find the best solution we can for this. The p dot equal 1 plus k x squared here. Now we're going to 1 plus k x squared times x dot. We have this x squared here, and let's see if we've got something else. Yeah, kx squared x dot minus ga kx. That's just the partial derivative of L with respect to x. And we notice this term right here. Let's see, yeah, p dot x has that. Anyway, we can work this down to a basically a oscillator equation with a force constant that's not constant. So this is the final result for getting the equation of motion with just the double derivative equal to the acceleration equal to, if I didn't have this stuff and this stuff right here, I would have a gravity times the curvature of the parabola that's making a constraint times x, but the rest of the equation is needed for cases where x is not very close to the bottom, or and also the velocity is fairly small. Then it would be just an oscillator, and that's kind of what we know about this system. But all this other stuff is now what we're going to do. I think what I'll do is I'll leave this result on the other screen, and we'll see if we get that result by the other methods. And that's a good way to compare the various ways to do the constraints. Now this one, this is really a screwy way. I don't think you'd find this in any other book, even one that used GCC. But what this one's good for is really giving you a feeling for what the various covariant and contravariant forces mean physically. The covariant one, as you recall, is a force that's proportional to gradients, and therefore, is that me? Oh dear. The idea is that those forces will be the frictionless constraints, and then friction will be the other ones, the ones that go along the tangent space. The forces that live in a tangent space are going to be ones that do work or take work, and friction is, of course, the first candidate for that. So what I'm going to do here is I'm going to say, okay, I'm going to make a crazy generalized curvilinear coordinate system in which the constraint is part of a series of possible coordinates that have simply been translated. That is, I'm going to have a y equal 1/2 kx squared. That's the one that it's going to be on, but we're going to have neighboring coordinate surfaces that have different values, and this is going to be our generalized curvilinear coordinate. We'll call it big Y for shorthand. And then I'm going to have just simply x equal a constant be the other coordinates, the lines parallel to that. So there's a non-orthogonal coordinate system, and we'll explore and review covariant versus contravariant by taking our queer coordinate number 1 to simply be the x-coordinate. So we have 3 notations here for the Q super 1. I'm going to use mostly the large uppercase X to indicate it. And this is our shorthand for that, so we don't have to write these indices in the algebra for this thing. And the algebra is extensive for this particular method, as you're going to see. But there's some advantages to seeing, first of all, how the forces work, how you can calculate what the constraint forces are. So far, we've made a big point about the Lagrangian method being a way to ignore constraints. And that's fine. But when you use a GCC, you get a chance to recover those sometimes automatically, the values of those constraints. That's a definite practical value if you're building a roller coaster. in trying to ignore the constraints, you'd better not open the park for a business until you've calculated what the constraint forces are and whether your apparatus can hold them without killing somebody. So what we're doing here is defining the Q1 and the Q2 to be these coordinate lines right here. One's absolutely straight, the other is curved. Only at this line here are they actually orthogonal. Everywhere else they make some kind of an angle. So that's our definition of these things, and what we do is go ahead and calculate the covariant unit, not unitary or whatever you want to call these GCC vectors. That means we calculate the Jacobian matrix, partial derivative of our Cartesian coordinates in which this problem is embedded with respect to the GCC that we've chosen here, namely this one just equal to x, so that's very simple. You get a 1 there and a 0 there. But for the y, which has x, Cartesian x in it, I get two components of the Jacobian matrix, kx and 1. So I get a E sub first GCC, which is uppercase x. I'll just call that x mostly from now on. That's 1 and k times x. That covariant vector right here, you can see it, it would start out pointing the way x vectors point, but then it would just follow the line up. So it's the one that's tangent to the surface of interest. The EY here is just 0, 1. Well, it's tangent to the y, big Y coordinates. Everywhere it goes, it's always pointing straight up. Okay? Now, the duals to these, if these are the kets, what are the bras? That's the Kajobian that's made out of the contravariant vectors in the rows. Here's one vector and there's the other. Okay? Now, the inversion of this matrix is really simple here. Basically, all I did was switch the ones, which did nothing at all, and then put a minus on the off diagonals. Well, there's the only thing that is affected by a minus, so that's pretty easy. This is a nice problem that way. And then I read off the contravariant, second contravariant vector, and here's the first. Okay, so here's E super x. Okay, now see, E super x just simply points with unit value along the original little x axis, that is, it's perpendicular to big X equal a constant. And then the other one, the EY, it's orthogonal to this one. That is, it's always pointing normal, you say. Okay. So now once you see the geometry of this, you see what I was talking about before is we're going to be talking about constraint forces that generally will be along this direction only if there's no friction. If there is some friction, well, then this is the vector that's going to carry it. You see, E super y and E sub x. We'll get to that later on, but that's what's neat about this is it's a hell of a mess, a crazy way. You wouldn't want to waste your time on a qualifying exam probably doing this, but it's a nice way to understand how you would do more mechanics than just frictionless problems. Okay, that's practical advantage. Now, the first coordinate differentials, of course, are going to use those same matrices. That's, remember, lemma 1 there. So we'll be expressing our new coordinates in terms of the old Cartesians right there. And then the kinetic coefficients, what we call Greek G AB, the Jacobian products, the Jacobian transform product. that is what we've got right here. This is just the xx, xy, those two have to be equal, and then this guy right here, y, y, that one is just this vector right here, very simple one. And let's see if there's anything else I need to say about that. I'm just using these two vectors to get those coefficients by dot product. Okay. Then here comes the contravariant metric. If you're going to do a Hamiltonian or a Riemann equation, you need that one. That's just the inverse of this one. Or you can redo it by calculating the dot products and check yourself. So, kinetic energy consists of, if you're going to use the Lagrangian approach with the velocities, you're going to use the gamma sub, that is the covariant metrics, to get it. And there's our kinetic energy expressed in the velocity form. And here's the whole Lagrangian with mgy, assuming gravity is straight down these vertical lines here, but that's y plus k x squared over 2. So we get this potential along with a fairly complicated Lagrangian. Now already you can see we haven't even gotten to the point of writing a complete equation of motion yet. We've got a lot of algebra when we're doing something like this. So this is definitely not a convenient way to do constraints, but let's bear with me. What we've got here are the first Lagrange equations, namely momentum equal partial derivative with respect to the velocities, and that comes out fairly nicely. Here, partial derivative with respect to x dot has that thing in it. And also the thing that involves y dot is there as well. So I've got that part in this matrix. And basically what I'm doing is just rewriting the covariant metric right here. But that is giving us momenta, which is by definition the partial with respect to velocities. Second Lagrange equations, p dot equal partial L with respect to q, plus, and this is the thing to remember for a general problem, we're talking about really the equation at the top center there where four-wheel drive garbage truck of mechanics, it can take any sort of force, and if we're going to have a force, we may, for each of these two momenta components, have a force component, and I'm just emphasizing its covariance by writing COV there, just to make a point about the distinction between those forces. Now, I'm taking the derivative here. That means I've got to take a derivative of the matrix times the velocity vector, and then add to that, that's this derivative right here times the velocity vector, and then take a derivative of that guy. Put that first. That's the acceleration vector. Here's the velocity vector. Okay, and here's whatever fictitious forces we have just because the coordinates are curved. And then finally, we're going to be adding something like that later on. But for the time, just to start with this, I'm just going to write the equations of motion as though the constraints weren't there. So all of this comes from the usual stuff that we've been doing. Partial derivative of L with respect to x and L with respect to y. That vector is gotten from each of these terms here. Okay, does that make sense so far? Now, as I say, no constraints added yet to these equations. Only gravity is in the mix here, okay? So the covariant force, these guys, are zero until we turn on the constraint. Right now it's free to move around in that coordinate manifold. And then we're going to turn the constraints on. We might as well get the algebra out of the way before we do that. So here's where the forces are going to be. Right now they're zero. And then there's this thing that we just calculated right here. All right, well, so a lot of cancellation occurs. It gets a little simpler, particularly with these two. Reduces, this cancels that, and then this comes out to be just that part there. We still have that thing to worry about. And then in the lower coordinate area, the minus times minus does plus, and so forth. So that is what we've got. And then I put them all together here in one big vector with accelerations and velocities there, each coming from their respective parts up here, now being added to this. And that's that. Okay, now, in order to get a contravariant, and that means Riemann equations, so that the second derivatives are exposed, we are going to go ahead and multiply by the contravariant metric coefficient matrix. That's this thing right here, the inverse of the covariant one. Yeah, the one that had the minuses. This one, and multiplying this part right here, which is equal to that, gives you this. Now, when this is cleaned up a little bit, you get a fairly simple result, having put these together there. Here's the inverse metric matrix. Here's that guy, and here's the acceleration. Now, exposed because the inverse canceled that thing to just give us acceleration. So this is a Riemann equation that's showing here. And that one very nicely, let's see if that's right. We've got to figure out, yes, this times that minus this times that, nothing. Same thing for that and that. So we end up with just this 1 and the G surviving with the Kx dot part there. And let's see if that is right. I think that's right, I think. And that's what we've got, I think, is x dot dot, y dot dot plus this is right now 0, but later on we're going to turn that stuff off. Okay. Now, if we do turn the contravariant forces on, this is the thing we just calculated. If we do turn the contravariant forces on, we're talking about components that are coefficients of normal vectors. So the normal vectors, E super y and then E super x, respectively normal to their assigned coordinate functions. This one, very simple function, x equal a constant. This one, a parabola equal a constant. Whereas, if you were to write the force that's driving this thing, gravity plus whatever the metal of the parabola is doing, you can just as well express it as contravariant components of covariant vectors. Covariant vectors are the tangents here, namely this guy and this guy right there. This one tangent to the x coordinate, this one tangent to this uppercase y coordinate. So these coefficients right here, I'm putting CON just to remind you that these are the other guys, the contras, that we'll be working with. So the difference is between a gradient, partial derivative of big X with respect to R. This one's partial R with respect to X. And same for the Y's. Okay, now, a frictionless constraint of the mass by that parabola y equal constant is normal to the parabola. That is, it's along the gradient. Okay? And the idea is that this force must have no component of anything else except that vector. So this is basically what that force will be. It will be proportional to this y, this gradient, the gradient of that frictionless surface or line that's holding keeping the mass in place. And let's see. Should mention that the sum total of requirements of the constraint are, first of all, what we just said, that this thing is 0, that's this thing, and this thing may not be 0. I'm not saying it absolutely is 0. There will be moments when the constraint isn't needed just instantaneously. But this is also important. If y is a constant, that coordinate system is a constant, these time derivatives can't be anything but 0 to all orders. So that's the main coordinate derivative constraint relationship right there. Okay. So once that is done, I can take that general equation that we just got a few slides back on slide 34. The y dot dot that I see in there, and there's two terms that have that, I'm going to set to 0. So I set that to 0, but the covariant forces, components, now are not 0. Okay, this one we know is 0, but this one is yet to be found. So we're carrying that constraint force through. This is something we haven't really done before. But while we're at it, if this is 0 right here, I've just gotten that equation that's on the other slide. Okay? So this is the solution to the thing way back on slide 12. So that's certainly a hard way to get there, because that just took a few lines, just took a whole bunch of stuff. Okay? But still, it's showing you the structure of the GCC, what it's really doing. It's revealing in a number of ways. And that comes next. The force that we're experiencing here is this covariant y, okay, times a E super y, and there's E super y, and this comes directly from that, okay? And we go ahead and use that one's x dot dot, and remember those two are the same thing. Recall the little x and big X are the same thing in this thing, so there isn't as much complexity. So I'm going to stick that in right here, stick that value here, and it's of course divided by 1 k squared x squared. And then we got this other stuff, okay, already have here. And this time I just made a common denominator, so I multiplied by that just to get something that I can add up. Anyway, that thing is the centripetal force, particularly at the bottom. At the bottom where x is equal to 0, right here at the bottom as we go right through that point right there. That's what you pay your money for on a roller coaster ride, is to either go through the bottom or over the top. In each of those cases, you're seeing here the actual centripetal force. This is the general case. It would be true all along the thing. This is the thing that's true at x equals 0. Very simple thing. Okay, so you've got gravity plus that. This velocity squared and m times the curvature. Curvature is the second derivative of this thing right here. That's why I put a half on it so it would make a nice clean number. here. Okay? So that's kind of a nice lesson in what's going on geometrically in any Lagrangian or Hamiltonian algebraic approach to this. All right, now here's another way. Way 3 is to use an orthogonal curvilinear coordinate system that has our constraint in it, a parabola. We've already looked a little bit at a coordinate system made entirely of parabolas. In fact, orthogonal parabolas. This was one of our sort of favorite complex variable functions. Z equal w squared, or its inverse, w equal the square root of z. Back in chapter 11 of unit 1, where we I showed you how you could get an OCC coordinate system from any function you like, such as z equal w squared or square root of z. And this is a really nice one that represents all kinds of things, but for one thing it represents the streamlines around a piece of metal that stops at the origin, or the flow of a incompressible fluid that comes around a pier. River could be coming this way and then goes around the pier and goes back. And then these are the streaming potentials and equipotentials for that. So there are all kinds of, and of course the plot of this thing, and the z versus xy is a rather beautiful minimal surface of soap bubble film. So the physics and geometry of this has already been mentioned a little bit, but the algebra is interesting too, because you have the radial of a polar coordinate system r involved here, that is x squared plus y squared, consisting of u squared plus v squared squared, and you see that's the thing that's kind of neat about this one. This one is that the u plus v squared, you can write x equal u minus v squared, you can write y just 2uv, and you can write r, that is this thing right here, the square root of x squared plus y squared. Well, that's going to be u plus v, u squared plus v squared squared, which is a fourth power polynomial in the u's and the v's. They are, after all, related to each other by either a square root or a square, depending on which side of the relation you're looking at. So we take these two and solve for u, well, u squared anyway, and you'll notice that what I get by putting these two things together is either r plus x or r minus x is equal to either 2u squared, respectively, or 2v squared. Okay? And then r, once again, is the square root of x squared plus y squared. So there's a relationship which gives u's in terms of x's and y's, and the simplest relation is the x's and y's in terms of the u's and v's. Okay? So this was, like many complex variables, have algebraic solutions either way. But the Jacobian doesn't care about that. When we go to take derivatives of this thing, I'll be able to deal either way, just about equally. However, the classic equation for a parabola, the thing that 4y squared equal 4p times some variable. Well, in this case, what I do is I say, okay, it's 4u squared v squared. That's the y squared. That's this thing squared, okay? It's u squared times v squared. We already said that we can get v squared from this equation right here, u squared minus x. Or we can write it backwards, v squared u squared, and use this thing as the 4p of a parabola, and then this thing right here is the independent variable, v squared. So we've got two parabolas whose all parabolas in this whole pile of them use this point here as their focus. So everywhere on this line you'll see a slope of 45 degrees for both of them, plus or minus 45 degrees right on the y-axis. Okay. So this is a focus for everything here. Pretty interesting. It's called confocal parabolic coordinate system. Very beautiful. Okay. Now I want to show you an application of this that takes us outside of our the topic today, and that is the use of this coordinate system to write both a classical and finally a quantum equation of motion, that is a Schrodinger equation, for a problem that involves the Coulomb potential plus an electrostatic constant electric field. Coulomb Stark potential is the name. Don't like to use that name because Stark was a terrible Nazi, but he was a good physicist, so we take what we get from people. That's what we're working with here. Now here's the Jacobian. It's the same, about the same for both of them. But we need to work the details of it.
So what would be the form that potential? Is it 1 over r squared minus q e times?
Potential is 1 over r.
Oh yeah, potential is 1 over r.
Right, that's the Coulomb part.
Oh yeah, it's 1 over r.
And then the other one is just going to be a constant times x.
Oh, x, okay. So
or y.
Okay.
I mean, we'll be allowed to, rotate this thing very nicely. We'll just pick one direction though when we turn on the force. So we got to get the metric for this coordinate system. Now, the thing about doing this analytic production of coordinate systems is you always accept that the singularities get an orthogonal coordinate system. You get more than an orthogonal coordinate system. You get a coordinate system where the sort of the lengths, the two unit vectors have the same length. So it doesn't matter whether you're talking about EU.EU or EV.EV, that's GUU and GVV, they're both equal to 4u squared plus v squared. That's just a dot product of this vector with itself. The dot product of this with this will be 0 every time. And then the dot product of this thing with itself, that's VV, same thing. It's 4r, the radius. Okay, that's this r, x squared plus y squared square rooted. Okay? So that's kind of cool. And then the inverse of this matrix is just this thing divided by the determinant, which is 4u squared minus 4v squared, which is 4u squared plus v squared. Okay? Well, you just get 1 over 2r for this one. Here's the contravariant scalar product being taken here, and all it comes out to be is 1 over 4r. Okay? So that is kind of neat to look at, because what you're seeing is you're seeing the contravariant vectors getting bigger and bigger as I approach the singularity, and then falling off as I leave the singularity. This is a scale drawing of these vectors here. There is a point where I'm calling it the unit circle. If I'm on the unit circle, they actually define the boxes. Remember how the covariant vectors define the lattice very nearly, okay? Now, of course, it's bigger here than it is here, so it isn't perfect, but if it was infinitesimally talking about units of microns, it'd be really close. So here's the contravariant ones getting smaller as you go And the covariant ones are getting bigger. They start out real small in here. Okay, in fact, it's so curvy there that it isn't framing its cell very well. But as I get out here, it starts to frame its cell very nicely. You see. So these covariant vectors are the ones that actually frame the cell. These are inverse of those. Okay, just some more review, okay, of what we've been talking about before. But seeing it in a real live, useful setting is always helpful. Okay, so that's the metric that we'll be needing for the Lagrangian. Okay, the Lagrangian looks like that. But to do what I want to do here, I need the Hamiltonian, because I want to have something that's constant for the energy. So here's the Hamiltonian making use of the contravariant metric coefficients to have inverse R. Okay, so that's what that is right there, with a factor of 2 is the radius, just plain radius of the thing. Okay, now I want to do this atomic start orbits. Atomic orbital means Coulomb start perturbation. And this perturbation we can do exactly. We're going to have a potential that has K over R, and then some electric field in proper units times X. Okay, so that's what we're going to use. And we're going to use this expression for X and this expression for R. That's what's so cool about this. This is going to make a separable Hamiltonian. Separable for classical use, separable for, very much separable for quantum mechanical use, if you want to solve for the wave function. We won't go that far today, that's quite a chore. But you do get these beautiful parabolic wave functions that come out of the parabolic coordinate system. So it's something that's really worth looking at. If you want to do some advanced quantum mechanics, it's really beautiful. Get your Mathematica out and use this as a guide. So what we're seeing here is the kinetic part, which is this thing, and then the potential part, which is this thing. And we're going to write the potential part just as u squared minus v squared for the x, and then r is u squared plus v squared, but it's sitting in the denominator for Coulomb. And that is neat because I can then take it apart. I can put all the u parts of the thing right here, and then write all of the v parts right there. Okay, so this is a little piece of a Hamiltonian that has the independent variable u, and this one has an independent variable v. That is, v is independent of what u is doing. So whatever motion that I get the thing, the u's will go and do their thing. These will do their thing independent of where the u is. So this is a generalization of a normal mode that we'll be talking about a lot in the next unit, but it's in curvilinear domain. So what we can do is we can say, and I pulled the energy inside here, so I have a 0 is equal to this. Well, 0 must be equal to the sum of this, which has to be constant because this thing has to be independent of that. And the only way to be independent is not to change. So we have little sub-Hamiltonians here. One for u and one for v. Okay, they add up to 0. The actual total energy is sitting in there. And then everything in here is just functions of v. So this one's a function of u and that constant, e, the Hamiltonian total. All right? So this separability, this really, really cool. I'll just go through it again here real quickly. Because I've got this and this. And then I separate it. Okay? And if I were to set the start field 0, I'd better get harmonic oscillation. That's kind of cool. That this is a neat coordinate system just to solve the Coulomb problem, because then it'll be harmonic. If I just turn the epsilons off, turn that field off, this becomes a harmonic oscillator, which is, you know, what a Coulomb orbit is, but it's it's in this coordinate system. It really looks harmonic. I think that's a cool thing to notice all by itself. Now, what I'd like to show you here are those anharmonic potentials that govern each of the peaks. The U turning points are here, the V turning points are there. But I'd like you to just to see typical orbits of this system. For you know, it's not a perturbation problem. It's a complete exact solution, analytic solution of the orbits. So if we could swing over to, hate to ask you to do this, the screen that has this part on it, that I'm using the actual web-based Coulet application, and let me go ahead and run it a little bit, just so you can get a feeling for what happens. So I've got it set here, and this may be a little bit hard to see. I've got it set here for a Coulomb orbit, which has got a -1 coefficient, and the Coulomb constant's right in the middle of these settings here. The rest of these things, except for the start field, are not relevant to discussion here, but the start thing I've got right now is just a little bit, a 0.086. Now I'm going to try to run this thing, and the first thing I'm going to do is erase the paths, so that you can see there's a Coulomb orbit, and the Coulomb orbit is oscillating in the electric field. It's sort of waving in the wind, so to speak. The electric field is that away. Am I showing on the right thing? I'm afraid I've got the old one sitting here. I'm sorry. Let me stop here a minute and switch. Forgot to switch. Got to switch to the modern computer from the old guy. I'll see if that shows up here. Show it in a minute. Okay, it's there. We're on. Okay, now I'm going to go ahead and run this thing. I'll start it off with an orbit, with an initial momentum like that, and I make orbits that simply oscillate in the wind. The electric field is tending to drive this thing this way on the screen there. It's driving it that way on the computer. But it's driving it toward me. The electric field is driving, whoops, and that time I hit the center and it went crazy. So we'll reset and erase the paths here. So there you see an orbit that it's basically just, as soon as it gets up here, it has a force that sort of brings it back. But it also changes the orbit parameters. It makes it less eccentric as it's going through the center there. Now, and then it gets eccentric here. In fact, it gets so eccentric that it bounces perfectly off of the thing. We haven't solved that bug yet quite. But okay, now I'm going to pause it just a little bit here and turn up the start field just a little bit. It's a 0.86. This is a clumsy setting. I'm going to turn to 0.1 and see, without changing the Coulomb constant, how this behaves. You see it, it's more quickly, it should oscillate more rapidly for the initial things that I've given it. That time it managed to survive collision with the core of the nucleus. Now, as you should be able to change these things. I'm going to take it up. Whoops, that's too much, probably. Let's see if Yeah, we've gone out of the potential. But this way, you see, it oscillates very, very fast. I'm closer into the Coulomb, so I'm not escaping. I haven't reached the local escape velocity of that. Or if I just pause this, erase the paths here, and pause again, and start off here, just give it a little bit of a, you get some pretty weird orbits. They're more like the second figure in the slide. This one is eventually going to conform to two parabolas. I think you can start to see it. It's being held between two parabolas rather nicely. Actually, this looks like it escaped from there. But that's more like this set of orbits right here. So this is a really non-trivial classical mechanical problem that has a really beautiful quantum solution to go with it. So I highly recommend it. Now the other one, we looked a little bit at elliptical hyperbolic coordinates. This was something that involved the square root of x squared minus a squared, z equal. Actually, it's arc cosine is the best way to express it. W arc cosine of z. The thing for that one is a model of a single electron with two nuclei to do Coulomb orbits. And this is just one end of that. You imagine that there's another focal point way, way down there. That's the orbits of a molecular ion. And you see the other ion is just giving us a Stark field here. And then this thing could make it way down the other one where it's so far away from this one that all it sees is a Stark field. So that it makes the Coulomb field into a uniform field when you get far enough away from it. So there's a lot of physics in that one too. Okay, now let's take on our problem using a third method. Let's count the methods. First one's direct, which gives us the solution immediately. The second one is to really go into the covariant contravariant coordinates and get frictional forces, or get a frictional force equation if you needed one, or get a thing that tells you what the constraint forces are. This one kind of does that too, but a little more efficiently. This is the Lagrange multiplier, or lambda for Lagrange, Greek L for Lagrange method. And the constraining parabola is again y equal 1/2 kx squared. There it is with the stuff that we used last time, the covariant contravariant vectors. But this time, what I call stupid parabolic as opposed to the smart parabolic that we just finished here, we're going to just say, okay, I got a constraint, what are we going to do with it? Imagine this is a coordinate line, its normal constraining force is along the gradient, just like we've been saying about the covariance, covariant unitary vectors, okay? So whatever that constraining force is, it has to be proportional, and that's the Lagrangian multiplier of the gradient of the constraint, the gradient of 1/2 kx squared minus y. The constraint is y equal 1/2 kx squared, and we're interested in the gradient of that thing, which is numerically 0, but the function isn't 0. We remember the derivative is the thing you're worried about in mechanics. So I have an equation that looks like this: lambda partial derivative of the constraint. We only have one, so I'm putting a 1 on it, because we'll talk about having more than 1 later. And here's the gradient, partial x, partial y in vector form. Okay? So that's lambda times kx minus 1. That's pretty simple. And we're going to use this force in an equation of motion. The proportionality factor is the Lagrange multiplier, Basically, it's like a covariant component. Okay. Now, yeah, that's just saying basically what I've said. This is as though it were a coordinate line. Okay, but we don't have to worry about its companions. The Newton-Cartesian equations, this thing, add a constant force to whatever this constraint force was. Okay, so we're going to have some coefficient of that gradient. Okay, so here's the equation of motion. Here's what it would be without any constraint. It would just be gravity in the y direction. X would just drift. And now we got this. Okay, and there's something as function of x, so that makes it non-trivial. Right? Constraint function, 1/2 kx squared has these derivatives. That's what we had to do before when we did the very first method. And we can stick those into the equation of motion. Y dot is this. Okay? Y dot is this. So we go ahead and set it equal to this particular one. We're getting rid of the y's this time, writing everything in terms of x. And there's the Lagrange multiplier, and there's the gravity. Okay? So you get an equation that looks like that. That is lambda here. Well, the only problem with this method is you've got to find lambda. Okay? Well, that's pretty easy to do. Just usually it's easy to do, particularly since it comes in linearly. So you are getting here lambda equal m blah 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 blah. Okay, now we can go back and substitute that into the equation of motion. Mx dot dot equals lambda kx. There it is. There's the lambda and the kx. Pretty slick. Okay? We're essentially done. There's the x dot dot. There's that thing that's in the numerator of that thing we got on the very first try. Again, same equation as on the 12th page. Make sense? So this is recommended for, high-speed work. But you should test it against if you can, do it that way, go do that way, and then come back and do it again this way on problems like this. That would be my recommendation. Now I'd like to say a few things about Lagrange multipliers that tie in with the next unit where we're going to be doing eigenvalue problems. This is just a calculus problem. Suppose you need to find the maximum of our quadratic form that we worked with for many things at the beginning of chapter 1 through, roughly speaking, 7, where we looked at the maximum or minimum subject to a constraint. Okay, in this case, let's say that the constraint have to be on a circle. Okay, this green circle here. So you demand that thing be constant, then you're looking for the maximum values. And imagine a bowl coming up here, and you've just drawn a circle in that bowl where it's you want that particular thing to always be the same height, so to speak. Okay? So the contact points have to satisfy proportionality relation involving the gradient. So here's an algebraic use of the Lagrange multiplier. I'm saying that the gradient of this h for Hamiltonian, but quadratic form in this case, there could be a cubic, quartic, cosine, sine, you name it, whatever function that is, and then we're going to be talking about where is the points where it will be an extremum. It may be a maximum, maybe a minimum, maybe neither. But one thing you want is that the gradient, whatever that is, point in the same direction as the gradient of this thing. Okay, in this case, that would come down to this. If I take the partial x of the quadratic form, I get this. I take the partial y of that, I get that. And that's a matrix equation in this case. You see, with the quadratic form, this becomes a linear left-hand side of the constraint equation. And then the right-hand side is simply an eigenvalue equation. Right? So this is the basic idea that eigenvalue equations are finding extremum of all the possibilities that Hamiltonian can make. Maximum and minimum. All you get with a 2x2 usually, but with 3x3 you're going to get a maximum, an intermediate, and a minimum. And the intermediate will be neither a maximum nor a minimum. It will be on a saddle. Then 4 dimensions you get all sorts of weird topologies for each of the eigenvector and eigenvalue pairs. Anyway, this does explain one thing, the etymology of the use of lambda for eigenvalues in so many textbooks. Right? Lagrange. Right? I haven't seen that written anywhere, but it sure looks like it happened that way. Okay. Now, as I point out here, eigenvalues means own values, and we're going to talk about that in Unit 4 using our projection methods on the thing. Now, what about multiple multipliers? And we're just about done here on this discussion, but I'd like to make sure that you see this, just so you're aware of it, because if you do any sort of Fokker-Plonk work or anything in statistical mechanics or a lot of things in quantum optics that require that sort of thinking, you're going to run into something like this. And this is a case where you have these constraints that don't pay any attention to GCC lines. It's just some other curve that's in a GCC coordinate system already. We were doing a Hamiltonian just in the last slide here that was elliptical. It could have been hyperbolic as well, or it could be higher ordered. In any case, the idea is that you have a gradient. It can be either written in Cartesian coordinates or in generalized coordinates. And the deal is that your Lagrange equations, P dot minus the partial with respect to the Q, which would, if there were no constraint forces at all, would be 0, but now we're going to turn some constraints on, then the Lagrange equations will have that as a forcing term. So we'll get as many as there are degrees of freedom equations of this form, but for a single lambda if there's only one constraint. So it's in the case of a two-dimensional thing, there would be a curve whose gradient is matching, making sure that its force is always perpendicular, normal to the constraint curve. So that's the application if you have a single constraint. But if you have two constraints, you demand both this one and a second one. Okay? Well, if it's in two dimensions, that kills your dynamics, because it just says you have to be at the intersection of those two curves on a two-dimensional plane, and your mechanics is dead. But if it's in three dimensions, well, then it has to be the intersection of two surfaces, which forms a line. So then you have a constraining line defined by these two. And the force will have to be a linear combination of the gradients of these things. That is, it will be a sum of lambda 1 times the gradient of C1 and lambda 2 times the gradient of C2. And we're going to have to solve some equations to get the values, functional values of lambda 1 and lambda 2 to finish the problem. So that's the way it looks for two or more. You get a whole bunch of equations like that. Now what if the constraint is of the worst kind? What if it's non-whole law, non-mink? Okay, what does that mean? Well, this is a very common situation. These are constraints that involve differentials, which are not necessarily integrable. The most famous constraint would be the constraint between the rotations of two wheels on a bicycle. Wherever the bicycle is going straight, I can write a function that tells me, given the initial settings of the wheels, where the other ones are going. Namely, the bicycle would demand that each wheel turn in unison, right? But what if I turn the wheel a little bit on one, okay, so that it has to go further than the wheel on the back? Well, then you have a differential constraint. At each instant, the one on the back has to turn in proportion to the one in front. The proportionality depending on where you are in the configuration of the bicycle. You could have the thing at right angles where this one would turn and this one wouldn't turn at all because it would just pivot. That's what we mean by this. And then with four wheels on a car, okay, so I remember going to a garage to get my tires fixed in Los Angeles, and one of those cool Mexican guys with this fancy car that had all sorts of decoration. It was just a beautiful piece of work. And he wanted it to be absolutely perfect, so he asked the guy at the gas station to make sure that when he put these new tires on with a big Goodyear symbol on them, that the Goodyear symbol was on the top for all the tires. And the station guy didn't want to argue with him because he was paying probably many hundreds of dollars for all this stuff. And he said, okay, I'll do it. And then later on he confided, he says, how long does that last? And the guy in the gas station realized that he had a four-dimensional non-harmonic problem. The Latino probably hadn't had a classical mechanics class yet, but if he did, he would be shocked to learn. And I'm sure he learned in a few days that there was something wrong with that. Anyway, that's the situation that you would have where we have been talking about very nice integrable differentials, okay, just involving partial derivatives. But what if you just have any old damn function in front of the differentials? You see, that's the general differential constraint relations that you have to put up with. Okay, will you play the same game with these coefficients you play with the partial derivatives? You just write Lagrange multipliers for each one of those. They're still differentially like this. It's just that the darn things are going to be variable in functions of the inclinations of each of the coordinates. So, if the differential can't be integrated to give a constraint function, it's then called non. Well, now, I don't know what the etymology of that is, but you'll see it everywhere and constraints are discussed. Okay, and I'm just guessing that it means the integral ones are holonomic. And I have to ask, why do you need bigger words than just being integrable or integrable? Anyway, when you have a situation like that, okay, that's an integrability condition. That's just meaning that the constraint differentials are differentiable and the order doesn't matter. These are not necessarily equal. Okay, if they're not, you're definitely in this situation. Okay, well, this is the first lecture to end a few minutes early. Are there any questions or anything that you would like to go over again? This is one lecture where you really have to do some of this stuff yourself. So I've given you a couple of problems that will let you exercise a little bit of the first part. Later on, if we have time, we'll be talking about some things that exercise the later parts of this. But this is a very interesting classical problem. Constraints of this kind that are rigid, like our parabola with a bead on it, do not get along with quantum mechanics at all, simply because the very act of putting the bead in a delta x equal 0 situation causes the delta p to explode. So the waves are not going to put up with that. So constraint, how do you do constraints in quantum mechanics? Well, you do something else. This is not a possibility. You can't corral the waves any more than you can herd cats. So this is a very classical thing that we're talking about when we talk about constraints, particularly ones that are functional like that. Okay. We'll